Assistant Professor in the Department of ECE. Welcome you all for this lecture. Today we are going to learn about pulse modulation techniques in digital communication. So generally modulation, which is used for transmitting our signal for a very long distance. So generally we have our message signal which is in the low frequency. For transmitting very high distance is impossible. So we are going to use a high frequency carrier signal according with the low frequency message signal. In pulse modulation, so the carrier signal is in the form of pulse waveform. So this is the basic concept of pulse modulation. Here the modulated signal is a very low frequency signal. So the characteristics of carrier signal, either amplitude, width or position, is changed according to the modulating signal. The three common techniques of pulse modulating system is, first one, pulse amplitude modulation, then pulse width modulation, then pulse position modulation. Pulse amplitude modulation, so PAM, so which is used in Ethernet LAN and also in analog to digital converters. Pulse width modulation, PWM, so which is used in applications like DC motor speed control as well as in LED dimming applications. Pulse position modulation, PPM, so which is used in applications like optical communication, then in military radar and telemetry. Let me see one by one. The first one is pulse amplitude modulation. So simplest form of pulse modulation. The amplitude of a constant width, constant position pulse carrier signal is varied according to the amplitude of the modulating signal. So here we are going to change the amplitude. Basically, the modulating signal is sampled by the digital train of pulses and the process is based upon the sampling theorem. So pulse amplitude modulation is used in instrumentation systems and analog to digital converters for computer interfacing. So this is the modulating signal. So if you see, so this is your analog modulating signal. So after modulation, so you get the pulse amplitude modulation. So here the amplitudes getting changed. The amplitude of the carriers is changed in accordance with the modulating signal. So modulation in which the amplitude of pulses is varied in accordance with the modulating signal. So in modulating signal, this is the analog form. So after modulation, the pulse amplitude modulation is like this. So the amplitude of the pulse is getting varied. So if you see, so the amplitude gets varied. So pulse amplitude modulation, modulation in which the amplitude of pulses is varied in accordance with the modulating signal. So then the generation of pulse amplitude modulation. The pulses in the PAM signal may be of flat top type or natural type or ideal type. So out of all the three pulse amplitude modulation methods, the flat top PAM is most popular and widely used. In case of natural samples, pulse amplitude modulation signal, the pulse has varying top in accordance with the signal variation. When such type of pulse is received at the receiver, it is always contaminated by noise. So then it becomes quite difficult for us to determine the shape of the top of the pulse, and thus the amplitude detection of the pulse is not exact. The reason for using flat top pulse amplitude modulation is that during the transmission, the noise interferes with the top of the transmitted pulses, and this noise can be easily removed if the pulse amplitude pulses has flat top. So in generation of flat top pulse amplitude modulation, we have a sample and hold circuit, so which is used to produce the flat top sampled pulse amplitude modulation. So here we have sample and hold circuit. So in that we have FET switches, that is field effect transistor switches, and one capacitor. The sampling switch is closed for a short duration by a short pulse applied to the gate 1 of the transistor. if you see in this diagram, this is the sampling switch gate 1 and this is the discharge switch gate 2 and this is your capacitor. Right. So the sampling switch is closed for a short duration by a short pulse applied to the gate 1 of the transistor. During this period, so the capacitor is quickly charged up to voltage which is equal to the instantaneous sample value of the incoming signal. Now the sampling switch is open and the capacitor holds the charge. So the discharge switch is then closed by the pulse applied to gate 2 of the other transistor. So due to this, the capacitor here, the capacitor C, which is getting discharged to 0 volt and the discharge switches is then open and thus capacitor has no voltage. Hence the output of the sample and the whole circuit consists of a sequence of flat top samples. So if you see, so this is the flat top, the top of the pulse. So it is flat here. So this is called flat top pulse amplitude modulation. So the duration here, the duration of one pulse is considered as tau, and if you calculate the transmission bandwidth, so bandwidth which is always greater than your maximum frequency, so which is calculated as 1 by, so tau plus tau which is equal to 1 by 2 tau. The next part is demodulation, that is getting back the original signal. Demodulation of pulse amplitude signals. For pulse amplitude modulated signals, the demodulation is done using a holding circuit. So here, so you should get a received pulse amplitude modulated signal. So the first block is holding circuit and second one is low pass filter. So in this method, the received PAM signal is allowed to pass through a holding circuit and a low pass filter. So here the switch, so consider this is one switch, so which is closed after the arrival of the pulse and it is open at the end of the pulse. In this way, the capacitor is charged to the pulse amplitude value and it holds this value during the interval between the two pulses. Hence the sampled values are held as shown in figure. So now, so if you see, so this is your low pass filter output. So first initially after your holding circuit you should get this waveform. Okay, so by using this low pass filter, so we can smooth our signal original, thus you should get the original message signal. So hence after this holding circuit, so the output is smoothened, so by use of this low pass filter. So the next modulation technique is pulse width modulation, PWM. So from the name itself, so we are going to change the width of the carrier signal here. The technique of varying the width of the constant amplitude pulse proportional to the amplitude of the modulation signal. So here the amplitude of the pulse is constant, we are going to change the width. It is also known as pulse duration because width is related with duration. We are also called as a pulse duration modulation. Either the leading edge, trailing edge or both may be varied by the modulating signal. So pulse width modulation gives better signal to noise performance than when compared with the pulse amplitude, and similarly it has advantage when compared with pulse position also, that is the pulse area of varying width and therefore of varying power content. So PWM has a better advantage. PWM still works if synchronization between transmitter and receiver fails, so whereas PPM does not. So if you see, this is the difference between pulse amplitude modulation and pulse width. So here the amplitudes are changed but the width are same. Okay, but in pulse width modulation, so if you notice, so here all the amplitudes are constant but we are going to change the, here the width is low when compared to this one, so the width are changed. So modulation in which the duration of pulses is varied in accordance with the modulating signal is called PWM. So coming to the generation part of pulse width modulation signal, so here we should have one comparator, right, then short-tooth generator, then monostable multivibrator, that is to get about your pulse position modulation. So these are the steps which is used for generation in pulse position also. So first to get pulse width modulation, so you need one comparator. A sawtooth generator which generates a sawtooth signal of frequency fs, and this sawtooth signal is used as a sampling signal. Okay, so here you should have one sawtooth generator. So from this sawtooth generator we are going to generate a signal which is used as a sampling signal. It is applied to the inverting terminal of the comparator. So here this is a comparator. We have both non-inverting and inverting terminals, and this one is connected with the inverting terminal. The modulating signal x of t is applied to the non-inverting terminal of the same comparator. So the modulating signal, that is after modulation you should receive this modulating signal x of t. So this one is given as an input to the non-inverting input of comparator. The comparator output will remain high as long as the instantaneous amplitude of x of t is higher than that of your ramp signal. Okay, so this gives rise to PWM signal, that is pulse width modulated signal at the comparator output. So if you see this diagram, so this is your sawtooth waveform and this is your modulating signal x of t. Okay, so here we should get comparator output is pulse width modulation. So the leading edges of the pulse width modulation waveform coincide with the falling edges of the ramp signal. So here this is the falling edge. Okay, so the falling edge which should be coincide with the leading edge of the pulse width. So this is the leading edge. So it both the signal getting coincide, right? So the leading edges of pulse width modulated signal are always generated at fixed time instants. The occurrence of its trailing edges will depend upon the instantaneous amplitude of x of t. So this value depends upon what is the amplitude of this x of t. Okay, so therefore this pulse width modulated signal is said to be trailing edge modulated pulse width modulation because it depends upon the trailing edge of this ramp signal. So this is the output for pulse width modulated output after given to the comparator. So the next part is how you should detect the original signal. So detection of pulse width modulated signal. So in pulse width modulation detection part you should have pulse generator, then ramp generator, so reference pulse generator, clipper and low pass filter. Okay, so let me see one by one. So the pulse width modulated signal which is received at the input of the detection circuit is contaminated with noise because after a very long distance, so you should receive a PWM signal, so usually it is getting affected with the noise signal also. This signal is applied to pulse generator circuit which regenerates the pulse width modulated signal. So this one is given as an input. Okay, so for the regeneration of your pulse width modulated signal, the regenerated pulses are applied to a reference pulse generator. Here this after this output it should be given as input to the reference pulse generator. It produces a train of constant amplitude, constant with pulses. So here the reference pulse generator, it will produce amplitude, constant amplitude and constant with pulses. The next part is the regenerated PWM pulses are also applied to ramp generator. If you see, so here it is applied to the ramp generator. So at the output of it, we get a constant slope ramp for the duration of the pulse. The constant amplitude pulses at the output of the reference pulse generator are then added to the ramp signal. If you see in this figure, so here both the output are getting added. The output of the adder is then clipped off at a threshold level to generate the pulse amplitude modulated signal at the output of the clipper. So here if you see, yes, this clipper circuit which is used to clip off the extra amplitude. So a low pass filter is generally used to recover the original modulating signal back from the pulse amplitude modulated signal. So the next one, what are the advantages and disadvantages of pulse width modulation? If you see advantages, so less effect of noise, that is very good noise immunity. Synchronization between the transmitter and receiver is not essential in PWM. But coming to the disadvantages, due to the variable pulse width, the pulses have variable power contents, because here the width are different for each pulses. So the power also getting varied. This is one of the disadvantage. And another disadvantage is to avoid any waveform distortion, the bandwidth required for the pulse width modulated communication is very large when compared to bandwidth of your pulse amplitude modulated signal. The next technique is pulse position modulation. So from the name itself, so here we are going to change the position of the signal. So pulse position modulation is when the position of a constant width and constant amplitude pulse within the prescribed time slot is varied according to the amplitude of the modulating signal. So here, so when dealing with the width and amplitude, both are constant. So here we are going to change just the position of the signal. So it has the advantage of requiring constant transmitter power output, but the disadvantage of depending on transmitter and receiver synchronization. So it is one of the disadvantage, because both the transmitter and receiver should have a synchronization. Pulse position modulation has less noise due to amplitude changes, because the received pulse may be clipped at the receiver, thus removing the amplitude changes caused by noise. The position of the pulses is changed with respect to the position of the reference pulses. The pulse position modulation pulses can be derived from the pulse width modulation. So the very simple technique here is, so after getting your pulse width modulation, yes, so you can apply the monostable vibrator, so and you can convert it into a pulse position modulation. So if you see, so both the three techniques are described in this figure. So this is your original modulating signal, that is your message signal. So if you see, this is the pulse amplitude modulated signal. Okay, so pulse amplitude modulated. So here we should have different amplitude. The amplitude are getting varied. So for pulse width modulation, constant amplitudes are constant, but you have variable width. Okay. So the third one is pulse position modulation. So here amplitude is constant, width is also constant, but if you see the position, yes, the position of this pulse is differed when compared with this pulse. So similarly, so here the position is changed. Here also the position is changed. So modulation in which the temporal positions of the pulses are varied in accordance with some characteristics of the modulating signal, which is called pulse position modulation. So coming to the generation part of pulse position modulation signal. So the same as we discussed already in pulse width modulation. So you should have a comparator, non-inverting terminal and inverting terminal. A short-tooth generation waveform is given as an input to your inverting terminal. An input signal x of t, which is given as your input to the non-inverting terminal. The output of this comparator you should all get is pulse width modulation. So extra block that we are additionally added with this pulse width modulation output is monostable multivibrator. So after this monostable multivibrator, you should get your pulse position modulated signal. So let me see. So the pulse width modulation pulses obtained at the comparator output are applied to a monostable multivibrator. So generally the monostable is a negative edge triggering unit. So hence corresponding to each trailing edge of pulse width modulation signal, the monostable output goes high. it remains high for a fixed time decided by its own RC components, because in monostable multivibrator the time constant is very important. So the time constant tau, which is nothing but which depends upon this both RC component values. So it remains high for a fixed time. Thus, as the trailing edge of the pulse width modulation signal keeps shifting in proportion with the modulating signal x of t, the pulse position modulation pulses also keep shifting. So if you see, so here the trailing edges of this is the trailing edge, okay, so that is from positive to negative, trailing edge of the pulse width modulation signal, so which keeps shifting in proportion with the modulating signal. So this is already we discussed in pulse width modulation output. The pulse position modulations, if you additionally, so you should, after getting the monostable multivibrator, it remains high for a fixed time. So it only remains high for a fixed time. So then your width becomes constant, but the positions only change. If you see, this is the trailing edge of this pulse width modulated output. From the trailing edge, your pulse position modulation output should be obtained. Here this is the trailing edge. So from this trailing edge you should get the ppm waveform. So here also from the trailing edge you should get the ppm waveform. If you see, the positions of all these pulses getting varied. So this is the generation part of pulse position modulation signal. So coming to the demodulation part of pulse position modulation signal. So pulse position modulation, so you should get the same, there is nothing difference between the direction part of pulse width modulation and pulse position modulation. So only the extra content only. So here we should have extra one unit which is called an SR flip-flop. Okay, so let me see how it is used in demodulation of pulse position modulation signal. So in pulse position modulation we should obtain the pulses, so which is given as input to the pulse generator. So same reference pulse generator is also used in this. So the output of pulse generator which is given as input to your, so R, in SR flip-flop you should have two inputs, one is set input pin and another one is reset input pin. So the output of this pulse generator is given as input to the reset pin, and output of this reference pulse generator is given as input to the set pin. Okay. So the noise corrupted pulse position modulation waveform is received by the pulse position modulation demodulator circuit. So whenever you should get the modulated waveform, so all the modulated waveform which is corrupted by the noise, because it is communicated via a very long distance. So the pulse generator develops a pulsed waveform at its output of fixed duration and apply these pulses to the reset pin of this flip-flop, SR flip-flop. A fixed, here in reference pulse, a fixed period references pulses generated from the incoming ppm waveform, and this one is given as input to the set pin of the SR flip-flop. So due to this set and reset signals applied to the flip-flop, so we get a pulse width signal at its output. The pulse width demodulated signal can be demodulated using the PWM demodulator circuit. So after that you should get your original modulating signal, that is your message signal from the demodulator circuit. Okay, so in this lecture, so we summarize the content. So we discussed about pulse modulation techniques in digital communication. So we have so many applications so in digital communication. So as we have three types of modulation, pulse modulation techniques. So we should discuss about pulse amplitude modulation, pulse width modulation and pulse position modulation. So we should see all the generating part, how we should generate the pulse amplitude modulation, and how you should detect your pulse amplitude modulation. Similarly, for pulse width also we should discuss about the generation part and reduction part. So for pulse position also we should see, so both the generation part and reduction part, and we see some of the application areas where this pulse amplitude modulation, pulse width modulation and pulse position modulation is used. Thank you.